movie-like images that people would watch for entertainment.
A scene where Tony Stark sticks his hand inside that 3D gauntlet. And that was the beginning of the thought process that led to the technology we're talking about today.
You've solved the problem, so how does it work? Welcome to the Tech Transfer Podcast. I'm here today with Dr. Daniel Smalley to talk about the volumetric display technology, one of my favorite technologies. So Daniel, do you want to introduce yourself and tell us what does it do?
Yeah, my name's Daniel Smalley, Associate Professor of Electrical Engineering here at Brigham Young University. And we work on sci-fi displays, trying to make them reality. In particular, the Princess Leia projector is something that we, like many researchers, would love to see made real. This is something that really indicates for us that we're in the future.
So this is R2-D2 projecting Princess Leia.
Right.
You're my only
hope. That's exactly right. Yeah. And I apologize for international viewers because they often don't catch that cultural touchstone. But yeah, this idea of an image projected out into the air that can be seen from every angle and is just floating absent the presence of any screen. It's just present in the air.
I think you were inspired too, you said, by Iron Man, where he puts his arm down into the hologram.
Yeah, and the story there is I come from the world of holography, and I was very partisan growing up through that program. Well, I grew up believing that holography was the answer to every 3D challenge, that any cool three-dimensional image could be made using holography. But when I saw that, the scene where Tony Stark sticks his hand inside that 3D gauntlet, I knew that I had a problem, because that's an image that you can't make with a hologram, because the light has to come from that glowing table, bore through his arm to make the image of the top material in order to enter the eye for him to have seen, the full gauntlet. And I thought, well, maybe you could do that with little floating nanobots or something like that. And that was the beginning of the thought process that led to the technology we're talking about today.
Okay, and so you came from the MIT Media Lab a few years ago, and I remember when we first met, you told me you were working on this, and then you had the insight. You've solved the problem, so how does it work?
So we use a laser to drag a tiny particle through the air and illuminate it as it moves. And what this does is it creates an image by persistence of vision. And anybody who's tried to write their name with a sparkler on a summer evening as a child will be familiar with this idea. You take a glowing spot, and if you move it quickly enough, you can make a squiggly line. And so we basically do the same thing. We take a single point and we move it through a complicated path to make a vector image, a line image in the air. If we move it fast enough, we can make more and more complex images.
So with enough little lines, you can make any image, presumably?
Any vector image, yeah. Okay. Or if you have it moving up and down, you could make a raster image, and we've demonstrated that in some of our papers.
Okay, and just to be clear, the laser that's moving the particle around is invisible. It's a different laser that's lighting it up, right?
We have, in our earliest generation of display, we actually used 4 different lasers. There was one that was mostly invisible, 405 nanometers, right at the edge. It's a violet, right at the edge of our vision. And that was used to trap the particle. And then we used red, green, blue lasers to illuminate the particle to give us a full color gamut, a nice rich colors.
Okay, fantastic. So they're small currently, but you can make images in the air. What are the best commercial applications, do you think, for it?
Well, there are any time you want to be interactive and you want something with fine spatial precision, I think this technology really shines. Let's give some examples. Let's say that Elon Musk has doubled the number of satellites in the air, in space. And people worry about those satellites smashing into each other. And so you have people looking at screens, in many cases 2D screens, trying to decide if these things are going to smash into each other. It's much easier to see 2 glowing dots traveling in space in front of you, and then you'd be able to viscerally predict whether or not those 2 points would collide. So I think for a spatial visualization like that one, this technology, even if it's just a few particles, could be helpful.
Okay, so similarly, air traffic control or cruise ships or something, you could display over a globe, here's where objects are, and they all light up.
Exactly. And in medicine, for example, there's 100,000 people in the United States who die each year from deep vein thrombosis, incident on heart surgery. When you do heart surgery, you put a catheter up through your vasculature into your heart, and if the catheter rubs against the artery wall, you can get a spot, an abrasion that causes clotting and eventually death. So if you could visualize the artery wall just as a circle, so take a particle and you draw a circle, and then you take another particle and draw another circle that represents the head of the catheter, and then the practitioner could watch those heads and just kind of play the game of surgery, right, operation, and make sure that those two circles don't touch, then you may be able to actually save lives with a very simple visualization by preventing that kind of abrasion.
Okay, and ultimately in the long term, you could have things that are more movie-like, like images that people would watch for entertainment, and would be reproducing. Maybe we've talked about for medical before, like layers of an X-ray or an image of MRI of someone's body.
Yeah, exactly. And any image, I have to be careful with the absolutes because that was the mistake I made with holography. But almost any image I can think of from science fiction. The good news with this technology is scaled appropriately, it would make images that we would recognize. So often we see clickbait that claims to have created the Princess Leia projector. You click through, and there's this inevitable letdown when you realize that it's a Pepper's Ghost or something else. This old technology that really would not create the sense of a floating image in air.
That actually happened to me yesterday. I saw something from Consumer Electronics Show. Looked like it could be this. It's not.
Yeah, exactly. This technology is exactly what you're imagining. Scaled appropriately, it would be just as magical as what we see on television and in the movies.
Okay, and so for an entrepreneur or commercial collaborator who's looking at this and understanding the potential, what is the size of display now, or what are the capabilities?
So right now, for the longest time, our first generation display has been making essentially thumbnail-sized images. And we certainly have on paper ideas for creating head-sized, human-sized, and even building-sized displays. And nothing about our technology or our experimentation has suggested that those aren't possible, which is good news. For example, we for our first-generation technology, we'll take a laser, we'll move it through a 1-inch lens, and we'll deflect it off a moving 1-inch mirror, and that makes roughly 1-inch images. But you could scale that lens to maybe 6 inches, or scale the mirror to be 6 inches, and now you're making 6 to 12-inch images. So you certainly can do a simple scaling of the technology, but it's still moving around one particle. The real key to scaling this technology is to, instead of taking a simple particle and moving it through a complicated path, you want to get many particles and move them in a simple path. And this is what we've spent a lot of time working on. To make this happen, we need to optimize particles and traps. We need to find the particles that absorb light the best and the traps that are most efficient at using that light, so we can get the most particles in the air for a given wattage of light. For a given laser, we want the most particles possible. And how many particles could you suspend on a single laser right now? So our current record is 50 particles in the air at a time with a single laser. And so we can increase the number of particles by adding more lasers or by continuing this process of optimizing particles and traps. And
without going too far into your process, like when you suspend 50 particles, that's not like 50 in a row on a laser. They're spread out in the field, right?
That's right. So we use a diffractive beam splitter, and those can separate particles laterally, so in a line horizontally and a line vertically, or in the Z, or even all three. You can imagine having a cube, a cubic set of particle locations.
And one other thing that's special about the technology is you can create an image, but because they're lasers, it could be across the room, right? You can project it way over there in front of someone's face.
Yeah, that's exactly right. This is a wonderful thing about this particular technology is you're basically holding essentially a flashlight, and then at some distance from that flashlight, you have your image. There are other technologies that use acoustic waves, for example, to trap things in the air, but they have the downside that you have to have a sound coming from both sides of the particle at the same time. And so it's always got to be enclosed, more or less. It is possible with this technology to be not enclosed. I mean, you have your source inside R2-D2, it's projecting out into the air, and there's no need to have a special wall or table or chair doing something to make that image happen.
So the final device could be a box, like a projector, except just like R2-D2, it's projecting the image out in front of people.
Exactly, yeah.
So that's great. And let's talk about that competitor product for a second. I think the most similar thing, or the thing that seems most capable, is the acoustic one. I've seen it online, but every time I've seen it, it's like you described. It's a box. How does that one work, and what are the What are the pros and cons of the two?
So it's actually a pretty fantastic technology. What happens is you take what's essentially a speaker and you put it on top, and what's essentially a speaker and you put it on the bottom, and then you turn the frequency up to a frequency we can't hear. Our hearing stops, if you're young, at about 20 kilohertz. These will operate, above that at maybe 40 kilohertz. And the waves, the sound waves, when they smash into each other, they form what's called standing wave patterns. So instead of moving, they're now static, and there's areas of high intensity sound and low intensity sound, and you can trap particles between those areas. And then you can, by changing the phase of the sound or adjusting the signal, you can get the particles to move up and down. And in this way, you can raster and move particles around. If you have lots and lots of speakers on the bottom and lots of speakers on the top, you can get very complicated movement from these particles. And the nice thing is that these particles aren't 10 microns like the ones we use. They can be several millimeters, and they don't have to be they don't have to be just styrofoam. They've trapped spiders and screws. I mean, they'll construct little things with globs of glue. They'll take a little glob of glue that's been held. And the beautiful thing about this technology, I think, is that with those same speakers, you can create a tactile field so that you can feel things, right? You can create sound in the audible. So you got 3D touch, you've got 3D sound, and then as you're moving around these particles, you also have 3D vision. And so you really address these three most important senses all with the same technology, which is really nice.
And they're actually, from what I've seen, they're actually focusing on some use cases that are not visual displays, that some other applications of that technology. But and we might be reiterating here, but your volumetric technology, what can it do that one can't?
So the key here is the one you just mentioned, the fact that it's not bilateral, it's unilateral. We just need to control one side, and it moves out into space. And also, we're controlling particles that are very small as 10 microns or smaller. And so if you're thinking about pure resolution capacity, you're talking about creating an image that has roughly print resolution, like 1600 dpi. And that's something that it would be very difficult to accomplish with an acoustic system where the wavelengths are just so much bigger than the wavelengths of light.
Yeah. Okay, fantastic. So for the volumetric display technology that you invented, what are some of the limitations? Are there colors that we can't do, or what things would not be possible, do you think?
Well, there are certainly plenty of limitations, but color is not one of them. I mean, because it's laser illuminated right now, it's the most beautiful colors you can imagine. They can be highly saturated, but at the same time, they don't have the speckle issues that many laser displays have, because these particles are in constant motion, and they smooth out the speckle effect that you may have seen if you've looked at a laser television or a laser projector. So colors are beautiful. The limitations right now really are that those lasers are moving off in a direction. So there is one forbidden direction. You can look at it at every direction except one, and that's where the lasers are headed. You don't want your eye to be there. Okay. And that will require a little bit of intelligence on the part of the building of the display, but not insurmountable. And then, of course,
is the
size.
solution to that to have the device on the ground and project vertically?
So you could have one device on the ground project vertically. You could have multiple projectors that take turns depending on where the viewer is, just to make sure that it's always projecting in a different direction. And it still creates content in the same volume regardless of where the projector is, which is one of the really great things about this technology. The other thing we have been looking at and have written patents in this area of creating active particles that glow in and of themselves. So if we could trap with an infrared wavelength, our eyes have much higher tolerance to infrared than we do visible. So if we could trap with infrared and maybe pump an active semiconductor or have a fluorescent material that we just illuminate with just a little bit of UV, then you'd have a situation where you don't have that splash of color. You would just see the particle, and it would just glow in its color, and there wouldn't be anything on the walls that you would need to avoid.
Okay, super interesting. So part of the process of developing this is scaling it up so you can do larger displays. What's the roadmap for that? What needs to happen?
Yeah, so we want to go from these thumb-sized images to head-sized images to human to room, and the key is to trap more and more particles, which requires better particles and better traps. And while those are challenges, they're also opportunities. There are people everywhere who would love and have told us, quote, I just want to be part of the magic of making the Princess Leia display happen. And so I think there are commercial opportunities right now. And we have done hundreds of customer discovery interviews that suggest this is in fact the case. And that brings us to our beachhead market, which I think is the education toy market, in the which we bring people on to help us develop these and scale these displays. And let me tell you how that might happen. So during COVID, we wanted to continue testing different types of particles. There's an enormous number of particles that could work. And in fact, our best particle now was actually found by accident. During COVID, we handed out these test rigs so that people could be testing different particles. And individuals from external schools heard about that. They wanted to be involved, and they asked us for it, and we sent them. And then just by accident, they discovered particles that we had never thought of that worked 6 times better than our best particle in lab. And we thought, well, if we can just scale this process, we can develop a catalog of particles that work well. And so those test rigs became what is now the UFO trapper. So if you could imagine a little plastic UFO that has a laser coming out of the bottom of it that's focused to a trap point, and then you can introduce particles using a glass microscope slide into the bottom of this UFO, and occasionally we'll trap a particle in that light beam, so it looks like this UFO is abducting particles, so to speak. And so individuals, as young as 6 years old, have been able to use this device to test things that they find in their room or at school or outside. Pollen, cinnamon, yeast, all these things have been tested. And with just a few pilot schools, we've found that we've been able to discover trappable particles that we had never thought of that work just as well and have properties like our being less toxic and a little more safe than some of our best particles currently.
Okay, great. So that's product one, is the educational kit that's out there, that's in motion. The imagine like a hypothetical next product. So you were talking about monitoring satellites around the Earth. Say there's a market for that. Someone wants to have little plastic Earths, except you're illuminating particles that show where all the satellites are. Right, exactly. Orbiting the Earth. So how would that work? How much would it cost to create something like that? What might a commercial partner think about?
Yeah, so if you want to go to the next step, so once we have our catalog of working particles, things that work really well at relatively low powers, I think the next step, the follow-on market then becomes medical education display, which would overlap with a lot of what you just talked about. I think that there is a synergy between a traditional film hologram and this photophoretic trap display, these glowing dots. So a traditional hologram is a piece of film or a plate of glass that if you look into it, you'll see a richly detailed 3D image. If you've ever seen a good hologram, you'll know what I'm talking about. Yeah. And so you can but the downside is this film hologram is static. It doesn't move. But what you could do is you could create a film hologram of a terrain if you're a military person. Sure. And then, put it down on the table and then use our technology, take that little glowing dot and move it above the terrain to represent, a satellite or aircraft or enemy troop movements. Yeah. Where I think that the need is, based off of our customer discovery interviews, is in dental offices, for example. There's 200,000 dentists in the United States, and they compete often by signaling technological prowess. So if you've ever seen a 3D printer in the lobby of a dental office, this is what's going on. They want to show that they've got it. And they have a willingness to pay up to $10,000 to make this happen. So high willingness to pay, lots and lots of dentists. And so you could imagine taking a hologram of a person's mouth, of their teeth, basing it off of x-rays they're already making, and then putting it inside of a box and then interrogating that hologram with this little glowing dot that can demonstrate where the cavity is or where the braces are going to be and that sort of thing. Do this side of medical education. It doesn't have anywhere near the type of regulation that other type of medical displays would have. High willingness to pay. And it would be well within the capabilities of what we'd be able to do after a fully fleshed out first phase in the educational display space.
And if someone, in terms of cost of manufacture, to create something that moved around a single dot on a display like that, what do you think it would cost to create?
This would be, well below, at a $10,000 price point, you're probably looking at a few $100s to make that work.
Okay, fantastic. And so in the future, when you when you look forward to more complex versions of the product that are showing a video of something, like displaying video-like content, how do you create the content? And even now, with one particle, how do you program it where it should go?
Yeah, that's a good question, and it highlights one of the other great advantages of this technology. Holography, which is always the comparison and the control, is extremely computationally expensive, and most 3D is. You take one 3D or one 2D image, you multiply that by 1,000, and that's how much information you're going to need. With this technology, for every particle, you just need an X, Y, and a Z, a position, and a red, green, and blue value. So just those 6 pieces of information for every particle. So you just take the number of particles you have, you multiply it by 6, and that's like the number of bytes that you need to transmit. And so you could, with using just the information in the video card on your laptop, control enough particles to do an HD face, at full scale, do HD video call, Zoom with this disembodied head that can turn and look at people in the room. That the information required is relatively small compared to other 3D displays.
Okay, and with videos I've seen of the product working, I've seen it in person as well, but I've seen you like move a particle in a figure 8 in the air. Is that a little program running that has those 6 pieces of information?
Yeah, and in fact, it typically runs on something as simple as an Arduino. I mean, these really tiny embedded controllers with very minimal computational complexity. So yeah, it really is miles and miles away from the type of complexity issues that we typically deal with 3D displays. And it's adjustable. You can add and subtract particles and complexity to meet the bandwidth budget that you have.
Okay, and in terms of interactivity, you talked about the Soundwave, other technology where you can maybe feel the edges of things, so that's kind of cool. What would interactivity be like with the volumetric display?
Well, you have you're controlling a particle, a physical object, excuse me, and this object is not enclosed by any screen, and so it can just live in, on, and around physical objects. It's augmenting your physical environment. We're taking digital information and making it a physical part of the world around you. So at some philosophical level, you could say that we are taking from the dust and creating these objects.
Yeah.
So we have, for example, created a little man, a little stick man in the air that could walk across the tip of your finger and jump up and down. We're looking at models. Students in chemistry classes will use these models of molecules, and we're looking at drawing the bonds between those molecules. I mean, that's a complicated, tortuous object, but we can, with our lasers, get in anywhere that light can reach. We can put a particle there, and so we can put an image there. And if the light can't reach it, a person couldn't see it anyway, so it doesn't matter. Exactly, right? But I mean, you could imagine, there are applications that are beyond display where you wanted to do something, maybe carbonize a filament inside of a PCB that's way into a server that you can't reach with your fingers, but if you could shine a light in there, maybe you could have these particles do things there. So that line of sight is the only limitation, and that's a pretty expansive set of possibilities.
And what about tracking people? You talked about being inspired by the Iron Man wraparound hologram. You could conceivably track a person crossing the room, and the hologram stays around their arm, right?
Yeah, that's absolutely right. And the fact that we're already using structured light means that we could just pick off one of those laser beams, have it scan the space, and look at the reflection, and tell, without too much more complication, where people are, where they're moving, where their eyes are.
How much of a problem is wind? Like if you were outside doing advertising with the technology, would particles get blown away, or how does that work? Yeah,
this is not an outdoor technology yet, for sure. It was the typical first generation particle can withstand 1 liter per second of flow, which is you blowing gently on the volume. So you definitely can blow the particle out of the trap. We have been working on strategies where we have a reservoir of particles ready to go, so that as you're drawing, if you happen to drop the particle, it can immediately just go over, and before your eye can detect it, grab a particle and just continue drawing. And so you could imagine having an image, passing your hand through it, and basically knocking out all those particles, but having them replaced so quickly that it appears to be continuous. Now, some people have worried that this is introducing a lot of pollution into the air, but we did some back-of-the-envelope calculations and discovered that the individual watching the display is producing 30,000 more particles, 30,000 times more particles than the display itself under the worst conditions.
Okay, and that fixing the image before you notice that it's changed makes me think of refresh rate with the monitor. What kind of refresh rate is possible with the technology?
That is entirely a function of how well trapped the particles are and how quickly they're being rastered. So for a small image, we typically move the particle at roughly 1 to 2 meters per second. So you could do a 30 frame refresh roughly at that speed. But once you get to multiple particles, if you imagine a line of particles moving up and down, each particle only has to move a fraction of the distance it would in the case of a single particle. And so you can get much quicker refresh rates moving at a slower speed. And so the movement limitation is no longer as great when we go to a multi-particle system.
Okay, and I think the key is it can move fast enough that it's beating your eye. It's faster than human perception.
Yeah, that is the engineering hope for sure, and I think I think that's reasonable from what I've seen in the lab.
Okay, one issue we always run into with university technologies, especially software, is that our inventors will say, we've created the technology, but we can't provide support. We can't be doing these business functions. So if a business partner were to license the technology for some specific use, imagine one of the little ones we've talked about right now, what kind of support would they have from the lab, or how do you interact with companies?
So our lab is very interested in taking this technology all the way from the deepest research into the hands of consumers. And we've done that in the case of these educational kits, and we'd be happy to do it again for these follow-on markets of educational, medical display and beyond. And we have a roadmap. So the way that an individual might interface with our group and get support from us are myriad. So if you're a student, we have done I-Corps programs in the past. And I-Corps, through the National Science Foundation, requires that you create a team that includes students. So a great way to get involved, if you've got an idea that you'd like to pursue, is help us write an I-Corps proposal. That would be money to help flesh out that idea, talk to people to see if there's a real push or a real pull for that push, and that you'd become familiar with the technology. We could help get you started with prototypes. If you are more established warhorse in the commercialization space, and you're interested in just a delta improvement from what we're already doing, maybe a different type of educational display. The Capstone program is a wonderful way here at BYU to get 5 engineers working on a prototype, for a full academic year, and we've had great success with that. But if you want to do something more a little bit more ambitious, a little more risky, we have certainly had sponsored research from interested individuals in industry where we will spend a full summer or even a full year creating a prototype that you could, for example, show to a potential board of directors or to individuals you'd hope would fund an endeavor. All those things we have done, and would be happy to do again to get this technology out into the world.
Great. And I would imagine if someone were launching a startup company, they would probably apply for an SBIR grant of some type, apply to DARPA or whoever it is and get their potentially large funding for some kind of application.
That's exactly right. We're currently writing STTR and SBIR grants, and we would love to engage with more partners. And the NSF really does love when established industries show interest in these emerging technologies. And so if that represents you, then you'd be a fantastic partner for us on an STTR, SBIR.
Okay, well, fantastic. All right, well, that's about the time we've got, Daniel, but thanks for describing the technology. It's fantastic. When will we have R2-D2 projectors in our homes?
It's secretly in my house right now.
Oh, is it? Okay, perfect. Good, we need to commercialize that. Okay, great, but sometime in the not too distant future, so thanks a lot.
That's right. Okay, thank you.